Hey everyone, welcome to University of Winnipeg Chemistry 1112. We are in chapter 17, which is the last chapter we look at in our course. We are looking at the second lecture today, all about galvanic cells. So this is wu17lec2. A smart thing to do before you do this is to review a screencast I did for the grade 12 class, tinyurl.com/chemu7s2. There I go into the real nitty-gritty of how galvanic cells work, and I talk about the SRP table. The university course assumes you remember some of that, so rather than me making another screencast to say the stuff that you're going to look at, it's already there. So watch it. If you're bored by it, watch it in 1.5 time. I sound like Alvin from Alvin and the Chipmunks. Okay, so I'll wait. And we're back. Okay, so 17.3 galvanic cells. We have another name, by the way, for galvanic cell is voltaic cell. And as you watched in your tinyurl.com chemu7s2, they convert chemical energy into electrical energy. Different molecules thrust into different situations cause reactions to happen or not. We try to exploit that difference to create electricity. And so with this delta G stuff, we'll get to that later. You can have direct transfer of electrons. Here we have what's going on here in figure 17.5. We got some zinc in a solution, and it's a solid strip of zinc, and we got some copper ions dancing around. They see the zinc and they say, hey zinc, can I have some electrons? The zinc gives its electrons to the copper to form copper solids. So the copper 2+ is reduced. It takes the electrons from the zinc. The zinc is oxidized and starts coming into solution in this chemical reaction. We don't really call it dissolving. We call it a redox reaction. So the zinc loses its electrons and starts coming into solution, while at the same time the copper gobbles up those electrons. Now, that can all happen in one beaker, and that's interesting. We can start plating the zinc, or what's left of it, with copper. So that's one thing can be done. The other thing is to separate these into two electrode compartments, so to two half compartments, just call them compartments in oxidation and reduction, and you put a wire between them and some load, which then can be powered by the electrons now being forced to go through that wire as they go from the anode compartment to the cathode compartment. Okay, and that's the way electrons flow. And yes, and some of the stuff I'm saying you just saw and listened to in that exciting screencast ChemU7S2. But I have to repeat some of it because it just flows just like the electrons flow. And whenever electrons flow, always from an anode to cathode, that creates a current. So an electron flow creates a current. And so you can have direct electron transfer and indirect electron transfer. And here we show in figure 76. Notice I'm not going to read every little paragraph in here. I'm going to just get down to the nuts and bolts of it all. So the zinc is the anode. Anode is always oxidation. So oxidation takes place at the anode. And the copper 2+ gobbles up electrons, so that's reduction. And reduction always takes place at the cathode. So there's my direction of electron flow. So the electrons, some older books put a negative sign by the anode and a positive sign by the cathode because it's like there's electrons moving up here. But then they flow over and go to the copper. So I'm going to try to avoid doing that notation. And now we have to have something else between these for it to happen. And this is something, again, you just saw by watching that review lecture. It's called a salt bridge, and it's going to try to maintain the neutrality of each electrode compartment. See, if you have too much zinc 2 pluses built up in the anode, you're going to get an overpotential or a charge imbalance, all sorts of words they use. So you're going to have anions in a salt bridge. Potassium nitrate is often used, and the anions will flow into the anode to try to reduce all this buildup of positive charge. Meanwhile, back at the ranch, the potassium cation is going to start dripping in. This is a slow controlled process. Start dripping in to the cathode solution because you're losing copper 2 pluses. They're being reduced to form copper. So you're trying to balance that out, so you put the potassium plus in there. Without the salt bridge, the circuit is not complete and we don't get electron flow. Now the salt bridge could be a glass inverted U-tube. It could be one porous cup in another. It could be paper. There's different ways that it's done. It's not always a glass tube. I mean, you have a salt bridge in a everyday dry cell or battery, which is a collection of dry cells, and it's not a piece of glass inverted U-tube, right? It's this paper between the cathode and the anode. Okay, here we see a picture of a typical galvanic cell, and there's also, if you go on, just go on YouTube and type in galvanic cell animation, you can watch one on your own. If you want to see a curated set of videos about galvanic cell, tinyurl.com vmchem, that's the grade 12 chem, and then go into unit 7 vids, or vids U7 or U7 vids, and there's a bunch of videos about redox, and they're good. So take a look at that if you want a fancy animation. The cathode and the anode have electrodes, metal plates, and they have to be metal so that electricity is conducted. Now, sometimes the metals don't participate in the reaction, they're inert. If they do participate, they're called active electrodes. So here's something a little bit new over what we did in grade 12. So in the copper zinc, which is called a Daniell cell, by the way, D-I-N-I-E-L-L, named after some French guy, the electrodes are active. The copper and zinc do react, but in some electrodes, like the standard hydrogen electrode, SHE, you have platinum, because it's SHE has got hydrogen gas and aqueous hydrogen. I mean, the redox half reaction for the standard hydrogen electrode is 2H plus 2 electrons goes to H2 gas. So if you want to use that as one of the halves of your reaction, of your galvanic cell, well, what are you going to put your alligator clip copper conducting wire in, right? You don't just dip it in the water. That doesn't work. You have to hook it up to something metal, and that's where platinum comes in. So platinum is called a passive electrode. They are there to supply or accept electrons to complete the circuit, but they are not oxidized or reduce themselves, so they're called passive. So you can have active electrodes and passive electrodes, and you can have one half cell being an active electrode and the other half cell being passive. It's not like both of them have to be active or both of them have to be passive. You can have a mix. Okay, so here we see some example where you have passive electrodes over there. Okay. There's a standard hydrogen electrode. The pressure, by the way, in a standard hydrogen electrode is 1.0 bar, right? Because it's called standard hydrogen electrode, and a concentration of 1 molar. And we're going to learn, and you, again, if you watch that grade 12 YouTube, the E0 cell. So the standard cell voltage for the standard hydrogen electrode is 0.00 volts. So that's a good reference point. And metals underneath that standard reduction potential table entries underneath, they are going to be active metals, which means they will cause hydrogen gas to form. They will give electrons to the H+. Metals like gold, which are higher up on the SRP table, they will not give electrons to H+, so they are inactive metals, which makes them more valuable. Okay, so here again, components of the galvanic cell, and here we have a battery describing a galvanic cell. This is a lead storage battery. I don't know why they started with a more complicated one, but there it is. You can read that one on your own. I'm going to do a different one. Actually, I'm going to just keep going here. Let's do the Daniel cell one. Let's do that one. And then, so I'm going to do it right here. So I'm going to draw it. Typically, not always, but typically on the left, you put the anode. And remember, use the valve. So anode is where oxidation happens, in the room where it happened. And so the zinc goes to zinc 2 plus 2 electrons. And cathode is where the reduction happens. So copper 2 plus 2 electrons goes to copper. If I'm writing it and it's neutral, I'm going to assume it's solid. Oh, you know what? Let's not assume anything. I'll put there. I can certainly assume if it's an ion, it's going to be aqueous, okay? So here's my salt bridge. Let's use a different one this time. Let's use sodium nitrate. Okay, so we have 2 active electrodes here. In the anode, the active electrode is zinc. So we got solid zinc, and it's dipping into a zinc nitrate solution. I won't bother putting in the nitrate, just zinc 2 plus. Then in my cathode, I got copper, solid, and inside it, I got the copper 2 plus aqueous. Then I have, well, I can have a voltmeter. There's old school analog voltmeter, right, with an arrow, which is actually going to turn out to be 1.10 volts. So the electrons are going to flow from the anode through the voltmeter and whatever other load there is into the cathode, and copper 2 plus says, oh, I'm hungry for electrons, I want to be reduced. So cathode is where the reduction happens. So the overall process is written here, zinc plus copper 2 plus goes to zinc 2 plus copper. Now this is a pain in the neck to write all the time, this lovely diagram that I did. So there's a shorthand notation. So let me try to remember which goes where. I know that in the middle we put a double solidus. That's a fancy name for a double line there. And let's see. I think I have oxidation on the left-hand side. This is my called a cell diagram or cell notation. I don't know why they call it a cell diagram. To me, this thing I just drew is a cell diagram. So I'm going to have zinc solid, zinc 2 plus aqueous. Oh, I forgot to draw in here. The nitrates go here, and anions towards the anode, cations towards the cathode. Okay, and then on the other side, I mean, this one solid line vertical is a phase boundary. That's the shorthand we use. Then the reduction, I got copper 2 plus aqueous, and I put one line there, copper solid. Okay, so did I do it right? Yeah. Some books are a little finicky about things, and they put in the concentration. I mean, I'm assuming it's 1 molar unless told otherwise. Okay, you typically do not put in the spectator ions because it's shorthand, right? You just want to see where the action is. Okay, so now if you're just looking at 1 or 2 cells and that's it, then you can do these pretty drawings. But if you're looking at lots and lots of cells, then the cell notation that we just did with these vertical lines comes into be a very useful thing to do. If there's more than one species in the same phase, you just you put the reactants first, then the products, and you separate them by commas. So here we have iron is oxidized. MnO4- is a great oxidizing agent, causes iron to be oxidized, and it is reduced. So then you have this overall process. Where's my... I need a passive electrode. There's no solid metals, are there? It's all aqueous, so I need passive electrodes in both parts. So here they are. Okay, so oxidation first. So I got Fe2 plus and Fe3 plus. Okay, so they're both dancing around in the oxidation half cell. Okay, so I have a little comma there between them. Reactant first and then product. Then the salt bridge represented by the double vertical lines. And then in the reduction, I got the MnO4-, an H+, MnO4-, H+, and an Mn2+. Typically, you don't put in the liquid water. Okay, so you're saying, "Oh, that's lots to write." Yeah, well, yeah, but it's what you do, and if you were to draw that, it would take you more time. So here's another example. We got iron going to iron 2+ plus 2 electrons, and we got the dichromate plus 14H+ plus 6 electrons goes to 2Cr3+ plus 7H2O. Okay, so let's jump straight to that. So iron is a metal, so we can just put it there. We don't need platinum. Iron 2+ is swimming around in the solution. And that's it for oxidation. Reduction, we got the dichromate anion, H+, and Cr3+. So those are all aqueous, but you have to hook up your alligator clip to something. So we're going to put platinum solid has my passive electrode in the cathode compartment. Okay, now sometimes you have to work backwards. So here you're given a shorthand notation and you have to balance it. So I'm going to try to do it without looking at it. Oh, too late, I already looked at it. Okay, so the aluminum is oxidized, right? We see there, that's the oxidation. And the bromine is reduced. So now I just have to balance them. So I do 2 times the OHR, 3 times the RHR, add them together, and you end up with 2 Al solid plus 3 Br2 goes to 2 Al3 plus 6 Br minus. Okay, so let's try, not the lead acid battery, but let's try practice exercise 17.9b. We get to that page. (17.9b). Okay, so let's go to let's get some more room here. Go to a blank page here. So we got Br minus is oxidized to Br2 plus 2 electrons. Okay, so that's the oxidation half reaction. This is page 849, PEX 79. Page 849, PEX 79. And we have something else. What the heck's going on here? We got the reduction. So chromium's positive 6 and the dichromate and positive 3. So I got to have Cr2O72 minus goes to form Cr3 plus. Then I just got to balance it, right? So I'm going to put a 2 here, 7H2O here, 14H plus here, Then I have some electrons. Now, sometimes you can just look, this is a reduction, you can just look at a standard reduction potential table and it's already balanced for you, but not all the entries are there. So this is good practice to go through it this way. And I think I have to have 6 electrons here, and that'll balance it, right? 8, 6, 6, 7, 14, 14, good. Okay, and then I got to take 3 times the Br minus, so 6 Br minus goes to 3 Br2 plus 6 electrons. And now I'm going to cancel out the 6 electrons. And does anything else cancel? No. So I get 6 Br minus plus Cr2O7 2 minus plus 14H plus goes to 3 Br2 plus 2 Cr3 plus 7H2O. Okay, so you have to literally know things backwards and forwards. Okay, cell potentials, let's get into that. This is the SRP table, and potentials are measured in volts. And again, reading that review or watching that review YouTube that I did for the grade 12 should be good. Here's a picture. The cathode is at a lower potential. It's a positive sign, designating the electrons flow to this terminal from the negative anode terminal. Okay, so cathodes are given a positive sign. That's where electrons flow to. And so the potential is measured in volts. The cell voltage is the difference between the potentials. And the table, if we're talking about standard values, so 1 molar and 1 bar is listed nicely for you on page 853. I'm going to Xerox this page. Xerox is an old-fashioned name for photocopy. And there is a larger table at the back of the book, I believe. And on the internet, you can get even larger, more advanced ones. This is just a representative sampling on page 853, but I'll photocopy it so you can refer to it a lot. And there's lots in here. It's not just a list of numbers, but the ordering, the ones that want to be reduced the most are to the left of the arrow going up. So they want to be gobbling up electrons the most, which makes them the best oxidizing agents. If you want to be reduced the most, you want to cause the other thing to be oxidized the most so that you will gobble up the electrons. And then going down the right-hand side, so the product side of each arrow, you want to be reduced the least. You want to be oxidized the most. So lithium wants to be oxidized the most. F2 wants to be reduced the most. And entries lower down than other entries will spontaneously be oxidized. And we'll talk about delta G and all that in a little while. So here we have discussion of the standard electrical potential. I talked about that. I've already mentioned the 1.1 volts. And so there you have it. So zinc is at a higher potential than copper, and the value becomes 1.1 volts. So the standard hydrogen electrode is 0. The half reactions, we write the reduction. Everything's relative. Yes, that's for sure. Let's take a look at this one here. We have 2 things happening. The copper 2 plus is reduced and the hydrogen is oxidized. And so if I look at the chart, copper 2 plus goes to copper, it's 0.342 in the, okay, round to 0.34. So what we're doing on these pages is just showing how the table 17.1 has been constructed. So you make one where you make an assumption or two, and then everything builds on top of that. Okay. Oh yeah, many values appear in Appendix F. Side note, Chemical Rubber Company, Handbook of Chemistry and Physics. Where this is from, my grandfather in the 1970s and 60s did the mathematics section in the handbook. He taught in Ohio, in Akron, and this company was based in Cleveland, Ohio. So my grandfather would do the math tables for that. So growing up, we had these all over the house. So they were everywhere. So anyways, here we see how the standard reduction potential is, we have a high value, and then the volts go down, 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 all the way to lithium. Now, when are we going to get that? Here we go. Okay. Okay. To the biggest voltage you can get, the equation is this. In different books, write it different ways. E0 cell is E0 cathode entry minus E0 anode entry. Now, some books will flip things around and add them together, but the easiest way is, let's say I said, well, what's the greatest cell voltage I could have? Voltage being a difference in the potentials. So you take the fluorine, which is the highest one, 2.866, minus the lowest one, which is lithium, minus 3.040. So, oh, I lost my, oh, this has happened before, hasn't it? That's okay. 2.866 minus 3. 3.040. Not cathode. Minus a minus is a plus, right? So 2.866 plus 3.040. 5.906. You cannot create, under standard conditions, a galvanic cell, also known as voltaic cell, where you spontaneously form electricity by exploiting the difference and the desire to gobble up electrons greater than 5.9 volts. So someone could say, well, I've got a camera that's a 6-volt battery. Is it fluorine gas lithium? Well, lithium is used in lots of batteries, but not with fluorine, okay? So those are batteries. Those are collections of dry cells hooked up in series to create 6 volts, okay? Our everyday AA or AAA battery, that's a copper zinc battery. No, it's not. What am I saying? It's a carbon graphite zinc battery around 1.5 volts. So if you want 6 volts, you got to have 4 of those dry cells in series. Okay, that's just a more efficient way to try to work with fluorine gas in creating a battery. Is a very mucky, unstable situation. So you don't do that. Okay, you exploit series, parallel, some of the physics things that you've learned to get larger voltages. Okay, and as I was saying before, as I see it here, if I had silver plus and gold 3 plus, spontaneously what would happen is this would reduce any creature lower down to it spontaneously. So I'd end up with AU3 plus 3AG goes to AU plus 3AG plus. That happens spontaneously, and the E0 for that would be the gold entry, which is the fourth one down, 1, 2, 3, 4, 1.498 minus the silver entry, which is 0.8. Some students think, oh, they when they're balancing them, they multiply the silver by 3. Do I multiply the 0.8 by 3? The answer is no. The volts, you may remember from physics, is a joules per coulomb. Joule per coulomb. So if you're multiplying everything through, well, yeah, you got more energy, but you also got more charge. So being an intensive property, you don't multiply through by the 3. So it's not like delta H. The value would be, what's that? 1.498 minus 0.8, which is 0.698 volts. Okay, whenever E naught is positive, that means it's spontaneous. We're going to talk about delta G very soon. You see, here's my standard hydrogen electrode. So things like tin, if I throw tin into acid, like hydrochloric acid, we're going to get hydrogen gas forming because the tin will be oxidized. So we would have, let's write it out here. Oh, really? They want to use H3O plus? That's so annoying. I'm gonna go rogue here. Here's the way I write the standard hydrogen electrode. 2H plus 2 electrons goes to H2 gas. That's a pain what they're doing. And then, so the thing underneath is going to be oxidized. Sn goes to Sn2 plus 2 electrons. So you end up with Sn plus 2H plus goes to Sn2 plus hydrogen gas. So you may have learned when you first looked at acid-base chemistry in junior high that, oh, throw a metal into acid and you will always form a hydrogen gas. And now you see that that has to be qualified, and it's only the metals which are underneath the standard hydrogen electrode entry that spontaneously give you hydrogen gas. If I take copper, like solid copper, and put it in acid under standard conditions, I don't, because copper's higher up. But lead I do, tin I do, iron I do. Okay, and the value for that standard would, for the standard cell voltage for the tin would be 0 minus a minus 0.137, so 0.137. Okay, and there we have our a repetition of what I just talked about. So I'm not going to talk about it again, except to go straight to an example. Okay, so let's look at example 1710, and so I'm going to have to flip back and forth to that table 17.1 to get through that. Here we go. A galvanic cell can be constructed from a zinc electrode immersed in a solution of zinc sulfate and an iron electrode immersed in a solution of iron 2 sulfate. Okay, fine. What's the standard potential of the cell, and what is the spontaneous direction? Okay, so I look and I see that I want it to be spontaneous. So which one? The iron is not as negative as the zinc, so the iron must be higher up than the zinc. Now notice there's different irons I can talk about. There's Fe2 plus, Fe3 plus, but here they're talking about Fe2 plus, and yes, that is higher up than the zinc. So I will have then that the Fe2 plus will be the cathode, that compartment, and you'll flow from the zinc to the iron. Okay, so you see just at the end here, this is what's happening, is the Fe2 plus is reduced and the zinc is oxidized. This is a pretty one. All the balancing happens nicely. I don't have to do much of anything. Except flip the zinc. The zinc is oxidized. Fe2 plus is reduced. So just looking at the entry values, E naught a cell, the entry value for these are called couples. These things are each a couple. So it's minus 0.447 minus a minus 0.762, which is positive 0.315 volts. Okay? If instead I wanted to use a copper 2 plus couple instead of the zinc, well, copper 2 plus is that, where's that relative to the iron? Iron 2 plus. Okay, the copper 2 plus is higher up, isn't it? So it's going to be reduced. Its value is 2 above the She here, 0.342. So it's going to be 0.342 minus, which one's the iron? Minus 0.447. So 0.342 plus 0.447. It's 0.789 volts. Yes, that's the answer. Good. So that's the cell voltage, and the reaction is, let's just write it out, right? That's what we're going to need to write that out. So copper 2 plus is reduced, plus Fe goes to Fe 2 plus the copper. Okay. Conventions. Typically the temperatures are 25 degrees Celsius, 1 molar solute, 1 bar for gas. Electrons are the reactants when we write our SRP table. Standard reduction potential table, right? I call it SRP. I remember the old days when I was a student at Grand Park High School Chem, we had 2 tables on the bulletin boards. One was the standard reduction potential table, and one was the standard oxidation potential table. And they were just the reverses of each other, but I guess the chemical companies at the time thought, oh, you should have both of them. It's better for the kids to see both directions. But I think they just tried to sell you, upsell you, right? Twice as many of the charts that you really need. Standard potential is defined to be 0 volts. Okay, positive E0 cell means it's spontaneous. And so there you have it. Okay. Rechargeable nickel cadmium battery. Let's not bother with that. Not good for the environment. So I'm not going to bother with that. And should we try practice exercise 1711? What do you think? I didn't want to do the nickel cadmium battery one. Yeah, we can try this one. So cell is constructed with indium metal and a 1 molar solution of indium chloride in 1 component. Okay, the chloride's not going to do much. Indium's 3 plus 3 electrons goes to indium's solid. Now indium's probably not one that's listed in the table, is it? Let's take a look back on page 853. Search through with me for indium, and it is not there. Okay, well, guess what? That's what we have to find. Determine the net reaction and the standard potential for the indium 3 plus half reaction. Now, the other compartment is copper and copper sulfate, so that's a classic. So Cu plus 2 electrons goes to Cu2 plus, and that we have to look at the chart. So, of course, I'm writing it wrong. Cu2 plus 2 electrons goes to Cu. That's the tabulated value. So Cu2 plus 2 electrons goes to Cu. That is 0.342. Okay. The indium, I don't know what the value is. I do know that, however, the cell voltage is 0.680. Okay. Now, oh, here. I thought I was going to have to make a guess here, but it says the copper electrode is the cathode. That means it's going to be higher up. So 0.680 equals 0.342 minus the indium value. So the indium value is 0.342 minus 0.680. .342 minus 0.680, which is minus 0.338 volts. So that is the tabulated value for the indium standard reduction potential, and is less than the copper 2+ standard reduction potential. Therefore, we have a galvanic cell. Oh, they wanted to write the net reactions, so I'm going to try to do this in my head here. Indium is actually going to be oxidized, and I got to multiply the copper by 3, so I'm going to get, and the indium by 2, so 3 Cu2 plus 2In goes to 3 Cu, see you later, plus 2In 3 plus. Is that right? Let's see. 3 Cu2 plus 2In goes to 3 Cu plus 2In 3 plus. Okay, that looks good. And that's good enough for this. Our next section will be our third lecture. We'll do free energy and electrochemistry. Have fun. Hope you get a charge out of this.